Hi everybody, here is the video for discussion 3.3, spectroscopic identification of organic compounds. All right, so see how it says practice makes perfect here? That means this is entirely skill-based, and the more you practice the skills, the better you'll be at them. This is actually one of my favorite things to teach because it's the only thing that's what chemists do as opposed to what chemistry is. Now, I'm going to go through this kind of quick, so it's not super long video. If you have any questions, of course, you should be in class. All right, so first thing we're going to talk about is this thing called Index of Hydrogen Deficiency, which is abbreviated with the acronym IHD. Now, saturation to most people generally means soaked with water, full of water. But the term saturated really just means full. So an organic compound is said to be saturated when each of the carbon atoms is bonded to the maximum number of hydrogen atoms. In other words, full of hydrogen. So alkanes are considered saturated hydrocarbons, but since when we add double bonds, triple bonds, or make ring structures, we have to deduct hydrogen atoms, alkenes, alkynes, cycloalkanes, and all the functional group containing compounds are considered to be unsaturated organic compounds, well, with the exception of the ether. All right, so based on the ratio of carbon to hydrogen, the number of carbons to halogens, we can work out how many single or how many double bonds, triple bonds, and or ring structures we have in a molecule. That's known as the index of hydrogen deficiency. So there's two ways we can work out the IHD for a particular compound. One is by assigning an IHD value for each type of thing we see in the molecule, and the other way is using an equation. All right, so to assign an IHD based on the structure, each bond type is assigned an IHD, and then the sum of all those individual IHDs is the IHD for the compound. So each IHD unit counts as 2 hydrogen atoms lost. So a double bond has an IHD of 1. Because remember, if you add a double bond, each carbon atom can bond to 1 less hydrogen. All right, so for triple bonds, the IHD is 2, and for any ring structure, the IHD is 1. All right, so if we look at these different structures, in order to determine the IHD, we just have to count the number of rings and or double or triple bonds. So in benzene, we have 1 ring, and we'll talk about this more in Unit 3, sort of 3 double bonds for an IHD of 4. If we look at cyclobutane, there's 1 ring and 0 double bonds, so cyclobutane has an IHD of 1. If we look at cyclohexane, same deal as cyclobutane, there's 1 ring but no double bonds, so it has an IHD of 1. I recommend you take the moment, pause the video, and see if you can work out the IHD for the last 2. All right, so for cyclopentadiene, there's 1 ring with 2 double bonds, which gives you an IHD of 3. And finally, for aspirin, there is 1 ring and 1, 2, 3, 4, 5 double bonds for a total IHD of 6. Getting the IHD from the structure really isn't that bad, but really what we want to do is determine the structure from the IHD, which is a little bit more challenging. So to do that, we can use an equation. The equation is the IHD is equal to 1/2 times 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens plus the number of nitrogen, with X just being a bonded halogen. So it could be fluorine, chlorine, bromine, or iodine. So if we break down the individual parts, 1/2 times 2C plus 2 minus H is actually just the general formula for alkanes. If you had an alkane with 0 halogens or nitrogen atoms bonded, then the IHD would be 0, indicating that there are no multiple bonds or rings in that structure. If we just take methane, for example, methane is 1 carbon, 4 hydrogens. So 2 times 1 is 2 plus 2 is 4 minus the 4 hydrogens is 0, and 0 times 0.5 is 0. You can do that for any alkane, plug it into this equation, and you'll end up with an IHD of 0. X refers to a halogen, and each halogen deducts 1 hydrogen atom from a molecule. And if it's nitrogen, we add nitrogen because nitrogen will give us 1 hydrogen back, because nitrogen likes to make 3 bonds, So that amino group will be NH2 or NH, which means when you bond it, it always comes with a single hydrogen. All right, so benzene is an example on the previous slide, and we indicated that it had an IHD of 4. Well, if you plug the numbers of carbon and hydrogen into this equation, it becomes 1/2 times 2 times 6, which is 12, plus 2, which is 14, minus 6, which is 8, times 1/2 is equal to 4. If you do the same thing for aspirin on the previous slide, right? Aspirin is C, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I believe it's C9H8O, so C9 would be 18, plus 2 is 20, minus 8 is 12, and 12 times 0.5 is 6. So either way you slice it, you can use either way. All right, so why do we care about what we're doing in this unit? Well, most organic compounds have structural isomers, and different isomers have different chemical reactivity and different chemical properties. So it's useful to us to know which structures we are dealing with. So using spectroscopy, we can determine which functional groups are present in molecules. We can see how all the atoms in the molecule are arranged. We can get useful mass information and so forth. So spectral analysis is used to analyze criminal evidence in a forensic manner, to determine pollutants present in ecosystems, so in soils and water, and the development and testing of reference standards of food and medicine. So a reference standard just tells a company that makes a product whether or not they've got the right thing. For example, if you're Jif making peanut butter, you can get a reference standard for peanut butter. So every time they make a batch of peanut butter, they can compare it against that to make sure that it is what they purport that it is. So in this unit, we're going to use 3 types of spectra together, as well as the IHD to determine the structural formula for molecules. Now, in order to keep this video short, I'm going to go through each one pretty quick. Make sure you have an IB chemistry data booklet handy so you can refer to it as we go. All right, so the 3 types are infrared spectroscopy, HNMR spectroscopy, and mass spectrometry. So the infrared tells us which bonds we have present in a molecule. Because it tells us which bonds we have, infrared spectroscopy can be used to identify functional groups in molecules. You can find infrared data in section 20 of the data booklet. NMR spectroscopy tells us how all the hydrogen atoms in a molecule are arranged, and different types of hydrogen will produce a different kind of peak in the spectrum. You can find NMR data in section 21. And finally, mass spectrometry gives us mass data. So it'll tell us what the molar mass of the compound is, as well as the masses of fragments that could break off that molecule when the sample is zapped with the X-ray and the ionizing radiation. And you can find mass spectral fragments in section 22 of the data booklet. So in this discussion, I've kind of pulled individual chunks of the data booklet out, but if you're learning from this video, you want to make sure to have it handy so you can reference. All right, so let's first talk about infrared. Infrared spectroscopy works on the principle that bonds in molecules are not rigid and can be stretched or bent and made to vibrate. Hold on, the phone is ringing. I'm just going to pause for a second. That was so nice. One of my favorite former students came to see me. All right, so anyways, I think I was saying that bonds in molecules are not rigid. They can absorb energy and be stretched, bent, or made to vibrate. So polar bonds in molecules will absorb discrete wavelengths of infrared. Remember, infrared is what we feel as heat. So this is actually how the greenhouse effect works. The carbon dioxide molecule, the carbon oxygen bonds in carbon dioxide absorb that infrared, which causes them to vibrate and change the dipole moment. So non-polar bonds will not absorb infrared radiation. All right, so different bonds will absorb different wavelengths of infrared. So based on the wavelength of infrared absorbed, you can work out which bonds you have in your molecule. And if you know which bonds you have, you can determine which functional group or compound class you're working with. So here is an infrared spectrum of butanoic acid. So some quick things to note. The baseline for this spectrum is actually at the top. And what we see is dips, which represent the wavelength of infrared radiation absorbed. So we call them absorptions and not peaks. In the other 2 types of spectra, we talk about peaks. Here we talk about absorptions. So the wavelength of infrared is what appears on the x-axis. Now, wavelengths are typically measured in nanometers, but here we use inverse centimeters because it just makes the numbers more convenient. Transmittance, what's on the y-axis, is just the intensity of the signal. So if an absorption is referred to as strong, it means it's a deep absorption that goes at least halfway down to the bottom of the spectrum. So I would say these here are weak, whereas the other ones are strong because they go more than halfway. And absorptions could also be labeled as broad. If they're broad, they're kind of like this, more like a spoon than they are a knife. It's really important to note also that broad absorptions can actually swallow up more narrow ones. So if you see here this broad absorption, these little points are other absorptions that are just within that one big broad absorption. So again, let's look at butanoic acid. Here are the structure. Now the first thing we're going to work out is which polar bonds are present in the molecule. Now the bonds between carbon atoms are nonpolar, but the carbon-hydrogen bonds are slightly polar. The carbon-oxygen double bond in the carboxyl group is slightly polar, actually very polar. There's the carbon-oxygen single bond and the bond between oxygen and hydrogen. Each of these bonds will absorb infrared radiation and appear in this spectrum. What you see in the data booklet is the wave number or the point on the x-axis where those absorptions will appear. So this is just a little chunk of the data booklet that's been pulled out. If it's a carbon-oxygen single bond, then the absorption will appear somewhere between 1050 and 1410. So 1050 is right there. 11, 12, 13, 14. 1450 is here. So the carbon-oxygen absorption could be any one of those. Let's just say it's one in the middle. So this bond is responsible for one of those absorptions. The carbon-oxygen double bond appears between 1700 and 1750. So this one right here is for the carbon-oxygen double. The oxygen-hydrogen bond is the broad absorption. And when you look at your data booklet, you'll see there's two OH bonds, one for alcohols and one for carboxylic acids. Since this is a carboxylic acid, that broad absorption will show up between 2500 and 3000 on the spectrum, whereas the alcohol one will show up greater than 3200. And finally, the carbon-hydrogen bond will have an absorption somewhere between 2850 and 3090. So it's probably one of these little bumps right here. So this is kind of backwards. Here we know which bonds are present, and we're comparing them to the IR. Normally what you'll do is use the IR to determine which bonds are present. All right, so next we have mass spectrometry. We looked at mass spectra in Unit 2, where we devised the relative atomic mass of elements. So in this unit, we're actually going to use it for a couple different things. One, the peak that has the largest mass to charge ratio is what we call the molecular ion peak. Now, please refer, I got a little distracted by my student visiting, so my energy level has changed. But anyways, when a sample goes through the mass spectrometer, the sample is first blasted with X-rays. Those X-rays will knock electrons off from the structure, including electrons that are part of the chemical bonds within it. So the peak that has the largest mass to charge ratio, we call the molecular ion. Essentially what that is the molar mass of the compound. And remember, molar mass is denoted with a capital M, so that's why we use a capital M for the molecular ion peak. The positive charge just shows that it's a molecular ion. So because some of the electrons in the chemical bonds are knocked off by the X-rays, some of the molecules that are put in the sample are fragmented. They're broken apart. The masses of each fragment will also appear in the mass spec. And you can identify a compound or at least rule out what compound it could not be based on the masses of fragments. So you can find the masses of individual fragments in section 22 of the data booklet. So here we can look at the mass spectrum of one compound that could either be propanone or propanal. These two compounds are structural isomers of each other, which means they both have the same molecular formula, C3H6O, but they have different structures. So the question here says the mass spectrum of a compound with molecular formula C3H6O was collected and the following mass to charge values were measured. So we have one for 58, one at 29, and one at 15. Almost always, the highest mass to charge ratio is just the integer value of the molar mass of the compound. So we can look at that here. The molecular formula is C3H6O. Well, if we take 3 times 12 for the 3 carbons, 1 times 6 for the 6 hydrogens, plus 16, we get 58. So the mass to charge ratio of 58 is the molar mass of the compound. Since these are both structural isomers of each other, either one or both could produce that peak in the spectrum. Now, if we look at the mass to charge ratio of 29, you'll see that one in table 22 of the data booklet. Now, when you see that mass to charge ratio in a mass spectrum, it's either going to be an ethyl group that got fragmented off or the COH or the CHO in the aldehyde. So if we look at propanal, there's 2 different places where this molecule could be, or there's 2 different fragments that could produce that mass to charge ratio, because we have the CHO here in the aldehyde and the ethyl group here. Now, if we're going to produce a fragment, when these molecules are fragmented, the bonds are broken and bonds don't reform. So in order to get a particular fragment in the mass spec, it has to be a continuous piece. So let's look at propanone. If we broke that bond there, we would have one piece that has a mass of 15. That would leave behind whatever 58 minus 15 is. I'm not going to do the math because my brain is pretty much donezo at this point. If you broke both of those methyl groups off, you'd have a peak at 15 for each of them, but you'd then have a peak at 28 for the carbon, which is 12, plus the oxygen, which is 16. There's no continuous fragment you can make anywhere in that molecule that could produce that mass to charge ratio in the mass spec. So we already know that this has to be propanal and not propanone, because propanal can produce that fragment and propanone cannot. Finally, the mass to charge of 15, if you look in the data booklet, is for a methyl group. Now, both of them could produce that peak because they both feature methyl groups. So both could make the peaks at 15 and 58, but only the aldehyde could make the peak at 29, which means we use the mass spec to confirm that this compound was propanal. The final spectrum we're going to look at is the NMR spectrum. And what NMR stands for is nuclear magnetic resonance. So the NMR spectrum is by far the most useful of all of them. It will provide information on the different chemical environments of hydrogen. Well, chemical environments of hydrogen just refer to the way that hydrogen atoms are bonded to carbon atoms in a molecule. Hydrogen atoms that are attached to the same carbon atom, or hydrogen atoms that are indistinguishable from other carbon atoms in the same molecule, are in the same environment. So essentially, hydrogen atoms that are in the same environment are bonded exactly like other hydrogen atoms in the molecule. So unless you see a completely symmetrical or identical hydrogen atoms, if they're attached to different carbon atoms, they will be in different environments. So how does this work? Essentially, hydrogen atoms have spin states just like electrons, and they're all completely random. So the hydrogen atoms in a sample are exposed to really, really high-powered electromagnets. And what those magnets do is align all the hydrogen atoms in the same spin state. The machine then passes long wavelength radio frequencies through the sample, and the frequency of radio waves that flip the hydrogens back to their original configuration is what produces a peak in the spectrum. All right, so the placement of each peak is called the chemical shift, and the unit is parts per million. Take a minute and look at your data booklet in section 21 so you can see what we're looking at. So when we analyze the spectrum, the number of peaks in it is the same as the number of hydrogen environments in the molecule. So there'd be a peak in the spectrum for each environment. Now, chemical shifts are in a range. So when you look in the data booklet, and again, I'm not doing it here just to keep the video shorter, when you look in the data booklet, you're going to see a range where that hydrogen should show up in the spectrum. But the data booklet doesn't tell the whole story, because depending on other atoms that are present, it could actually shift those chemical shifts a little bit more. So oxygen is a big culprit because it has such a high electronegativity. The oxygen atoms will influence the electrons in the bonds between carbon and hydrogen. So essentially, it'll anchor them or hold on to them, which means that in order to flip them back to their original orientation, they need a higher frequency of radio waves. So if we look at propane versus propanone, if you look in the data booklet, methyl hydrogens would show up somewhere in the range of 0.9 to 1.0 parts per million. Well, in propanone, we have methyl hydrogens, but because those hydrogens are on carbon atoms that are adjacent to a carbonyl group, the chemical shift gets pushed a little bit further out in the spectrum to a range of 2.0 to 4. Again, we'll talk about this in more depth in class. Now, we don't have methyl hydrogens listed in the data booklet specifically for propanone. So if you're asked to identify certain hydrogens, it's important to consider their proximity to oxygen, because if those hydrogen atoms are close to an oxygen, then the range will be a little bit higher. All right, so when we count hydrogen environments, you just have to look at the hydrogen atoms and see how they are bonded. They have to be bonded exactly the same as other hydrogen atoms to be in the same environment. So if we look at methanoic acid, there are two hydrogens. One of them is bonded to oxygen and the other is bonded to carbon. Since they're not bonded identically, each hydrogen atom is in its own environment, giving us two, which means in the NMR spectrum of methanoic acid, we'll see two peaks. For pentane, now again, we don't see alkanes a lot because they're not distinct enough, but what we're going to look for to determine environments is symmetry. There's one obvious line of symmetry right down the middle of pentane. Now, to determine if hydrogens are in the same environment, imagine rotating the molecule around 180 degrees. If the molecule looks exactly the same, if those hydrogens are the same as they were before you rotated it, then they're in the same environment. Because we have that line of symmetry, all those hydrogens are in the same environment. Now, the same thing with the methylene hydrogens here. They are also in the same environment, and the hydrogens in the middle are in their own environment. Now, you could also describe the hydrogen atoms. So these are methylene hydrogen atoms that are bonded to a methyl group and a propyl group. So a methyl group on one side and a propyl group on the other. Well, if we look at the hydrogens on the other side of that line of symmetry, they are methylene hydrogens that are bonded to a methyl group and a propyl group. So you can describe them in the same way, so they're in the same environment. So since there are three different environments in this molecule, you will see three peaks in the spectrum. All right, so formaldehyde or methanal features two hydrogen atoms. They're both bonded to the same carbon atom, so they're in the same environment. Since there's one environment, you'll see one peak in the spectrum for methanal. Now, phenol is just a phenyl group bonded to a hydroxyl group. Now, because we have oxygen on one end, it completely throws off any symmetry. Now, remember, there's one hydrogen atom bonded to each of those. So the hydrogen that's bonded to the oxygen is in its own environment. And since there's a diagonal line of symmetry going through there, the hydrogen atoms on carbons 2 and 6, or 2 and 5, I can count, are in the same environment. And then the hydrogens on carbon 1, 2, 3, and 5 are in the same environment as well. The hydrogen that is opposite the oxygen is also in its own environment. So there are 4 hydrogen environments in phenol. So the NMR spectrum of phenol, you will see 4 peaks in the spectrum. Man, I feel like this video started out so good, then I got distracted and the ending is not as good, but whatever. All right, for propan-1-ol, notice there's oxygen at one end. That completely destroys any symmetry. So for each carbon, the hydrogens will be in their own environment. So 1, 2, 3, and 4. Since there's 4 environments, there'll be 4 peaks in the spectrum. And for 1,3-dichloropropionene, there are 3 carbons. Each carbon atom has hydrogens bonded to it. The carbon all the way to the right is bonded to a chlorine and 2 hydrogens. This carbon is bonded to 1 hydrogen, and this carbon is bonded to a hydrogen and a chlorine. Since all the hydrogens are bonded in different ways, they're all in their own environment. Remember, hydrogens attached to the same carbon are in the same environment, so those two are both in an environment. That one's all by itself, and that one is all by itself. Since there are 3, you have 3 peaks in the spectrum. All right, next, another piece of information that the NMR gives you is something called the integration trace. So the integration trace uses an integral symbol next to the peaks. Now, for those of you that take calculus, you'll know that essentially calculus is just calculating the area under a curve, right? So what the integration trace does is calculate the area underneath the peaks. Essentially what that does is gives us the ratio of hydrogen atoms in each environment. Now, because this is still a high school class, we give you pretty simple molecules. So almost always, the integration trace just tells you how many hydrogen atoms are in each environment. So if we go back to the previous slide, we can determine the integration trace. For propan-1-ol, it'll be 1 to 2 to 2 to 3, because there's 1 hydrogen in the blue environment, 2 in the red, 2 in the green, and 3 in the purple. For 1,3-dichloropropone, for the 3 peaks, the integration trace will be 1 to 1 to 2. 1 in the blue environment, 1 in the red environment, and 2 in the green environment. Finally, if you use a high-resolution NMR, you can zoom in on the peaks and see something called a splitting pattern. A splitting pattern just tells you what happens to the peaks. If they get split, then they get split into multiple points. So for each hydrogen environment, the splitting pattern tells you how many hydrogen atoms are on the adjacent atoms to that environment. So if there are no hydrogens on it, the peak in the spectrum will be a singlet. If there's 1 hydrogen on the neighboring atoms, then the peak will be a doublet. If there are 2, then it'll be a triplet. And if there are 3, it'll be a quartet. So what do I mean by that? If the peak is a singlet, it's just a single line, no splitting in it. If it's a doublet, the peak is split into 2 points. If it's a triplet, it's split into 3. And if it's a quartet, it's split into 4. Anything with more splitting than a quartet, we can just call complex. So if I look at the environments going right to left in this molecule, for the blue environment, it's the hydrogen bonded to this oxygen atom. To determine the splitting pattern for it, we have to look at the adjacent atom. If there are 2 hydrogens on it, then the splitting pattern will be a triplet. If we look at the next carbon atom, there are 2 atoms adjacent. One of them has 1 hydrogen and the other has 2. For 3 total hydrogens, so the peak in the spectrum for that red environment will be a quartet. If we look at the green environment, again, there are 2 adjacent atoms. On one atom, there's 2 hydrogens, and on the other, there's 3 for a grand total of 5, which means that the peak will be a sextet. Now, again, if it's greater than a quartet, you can just call it complex. And finally, for the purple environment, there's only 1 adjacent atom, and it has 2 hydrogens on it, so that peak will be a triplet. For 1,3-dichloropropone, I did the blue one first. If I wanted to determine the splitting pattern for this blue environment, I look at the adjacent carbon atom. Since there is 1 hydrogen atom on it, that will be a doublet. If I look at the red environment, it's in the middle of 2. So there's 2 adjacent carbons for a grand total of 1, 2, 3 hydrogens. So that peak will be a quartet. And finally, for the green environment, there's only 1 hydrogen on the neighboring atom. So that will be a doublet. All right, so let's actually look at a spectrum. This is for a compound with molecular formula C4H8O. So let's first actually look at the spectrum. What we see here are 3 peaks. There's one, there's another one, a little sloppy, and there's another one that's a little sloppy. Here are the integration traces. The integral symbol is just like a stretched out S. Now here they give us numbers. That means there's 3 hydrogens in one environment, 2 in another, and 3 in another. Now, sometimes you're not given the value of the integration trace. If that's the case, it's just the relative size of each. So if you cut this one with an integration trace of 2 in half, then this would be 2 units, and this one would be 3. So for that, we actually have to get out a ruler and measure. All right, so we see here the zoomed in on this peak. It's a quartet. When we zoom in on this one, it's a triplet. And there's no zooming on that one because it's just a singlet. So I know automatically that this molecule must have 3 hydrogen environments because we see 3 peaks in the spectrum. The ratio of hydrogens in each environment will be 3 to 2 to 3. The integration trace gives us that information. So let's look at each peak individually. This first peak over to the left is a singlet. There are 3 hydrogens in it. The integration trace tells me that, and the fact that it's a singlet tells me that next to that environment is an atom that does not have hydrogen atoms bonded to it. If I look at the second peak, First of all, there are 2 hydrogen atoms in it, you know, because the integration trace of 2. And since it's a quartet, the atoms adjacent to it on either side must have a total of 3 hydrogens on them. And finally, the peak over here to the right has 3 hydrogens in it. We get that from the integration trace. And the splitting pattern as a triplet tells us there are 2 hydrogen atoms on the neighboring atoms. This here is the molecule that produces this NMR. We can actually use this NMR to identify each environment. So first things first, the blue environment. I chose this one, first of all, because there are 1, 2, 3 hydrogen atoms in it. And if we look at the adjacent carbon atom, it's just bonded to oxygen and there's no hydrogens on it, which would give us that singlet. The red environment must be this one. First of all, there's 2 hydrogens in it, and it's the only environment with 2 hydrogen atoms, but the very fact that it's a quartet shows that there are 3 hydrogen atoms on the neighboring atoms. So this one has none, but this methyl group has 3, which would give it the quartet. Finally, the green environment is the environment at the end. I know that because there's 3 hydrogen atoms in it, and it's a triplet, and a triplet is formed when there are 2 hydrogen atoms on the neighboring atom. So the NMR gives us the most information. I went through all this really quickly, so we'll go through it in more depth in class. Finally, X-ray crystallography. It's a technique that we do not need to work with, but you have to know what it is. What an X-ray crystallograph does is reflect X-rays through a crystal surface. The way that those X-rays are reflected off the crystal structure tells you what the length of the bonds and the bond angles and bond lengths in the structures. So this is just study to know. You don't have to know anything about it, but you got to know what it is. Thanks for watching, and see everybody tomorrow in class.